So the following video talks about the simple collision theory, the idea being we need to appreciate how the collision theory explains reactions occurring, barriers to those reactions occurring, and the factors affecting those reactions and the rates of the reaction. Separate to that, I'll go on to talk about catalysts, their role with respect to the simple collision theory, with respect to reactions, some other parts of the syllabus, and then speak further about some specific examples required in this syllabus. So, for instance, the Haber process. Along with that, I'll go on to talk about ways to represent the activity of catalysts, to explain how they work, and then hopefully some Q&A before we go on to the actual Q&A video that has some detailed exam questions. So the collision theory. To begin with, let's appreciate a reaction. A reacts with BC, so they're bonded together, forming AB and then C. Now this reaction I've simplified, and no, there's no specific reactants and products because it's a theory I want to bring forward. Here's a beaker with A floating around, bits of A, and there's some BCs floating around, those compounds. Element A, BC compounds mixed together. If we now zoom in so we can see specific A's and BC's, I want to focus on what's about to happen. Now let me explain initially what the collision theory is. In order for particles to react, they must collide with enough energy that's greater than the activation energy and be orientated correctly. So if we take a further look and focus just on this pair and this pair of particles here. Here, A and B and C, when they're going to react, A is facing B. So effectively, they're orientated in the right direction. They can then react. However, this pair here, A is facing C, they're about to collide, but because A needs to react with B, they're not orientated in the right manner. Therefore, they will not go and react. They'll simply bounce away. So what we see here in the first example, A, B and C, orientated in the right manner. A can then react with B and become AB, leaving C to go on its merry way. Hope that makes sense. Now, the lack of correct orientation here prevents A from reacting with BC because it's facing C. It's about to collide with C. And therefore, this particle bounces away, goes on its merry way, and A stays as A. The collision theory requires us to appreciate that particles need to be orientated in the correct way in order for them to react. Otherwise, they'll simply bounce away. Secondly, these particles must have had enough energy to overcome what's called the activation energy, something we've come across in an earlier video. The idea that some minimum energy must be put into a reaction to break bonds in reactants. In this case, we've only got this particular bond to break. That activation energy must break that bond and allow a new bond to then form between these two. In order for that activation energy to be met, these particles that are floating around have a degree of kinetic energy as they're moving around. Therefore, that energy equates to, from a collision, the activation energy. But if they're moving around with not so much kinetic energy and not enough energy to overcome the activation energy, even if they're orientated in the right manner, they will not collide and react. As a result, simple collision theory requires us to appreciate A, B, C, our reactants, will react if they collide with energy greater than the activation energy and they're orientated in the correct manner. So let's stick to our ABC example. Again, we've got our beaker here, A reacting with particles of BC to form AB and then C. What factors affect the collision theory? First, I'm going to look at concentration. So let's increase the concentration of A, the concentration of BC, and here in this beaker I've tried to illustrate this, that there are more A and BCs floating around, moving around. They all have different amounts of energy. Increasing the concentration will allow more particles to move around. With more particles there would be more collisions. With more collisions, more successful collisions, i.e. collisions that led to a reaction because they were orientated in the right way and they had energy greater than the activation energy. Because there are more successful collisions, more products are produced, increasing the rate of reaction. So if in an exam you're asked to describe the effect using collision theory on the rate of reaction by increasing concentration, you would simply follow this logic.
Increasing concentration increases the number of particles, leading to more collisions and more successful collisions, producing more products, therefore increasing the rate of reaction. Simple. Increasing concentration doesn't have to be both. You could increase concentration of one or the other or both, will lead to a greater rate of reaction, as explained by the collision theory as we've just discussed. Let's look at pressure. So, with respect to pressure, now, what I hope you noticed is I've put gases now as my reactants and products, simply to illustrate that pressure has an influence on gaseous reactants and products. Now, it does have an influence on other reactions as well, but as far as your syllabus is concerned, we're only going to be looking at gaseous particles. So, let's imagine now I have a beaker with gaseous A and gaseous BC. This represents an airtight seal, this being a sort of a lid with these gases flying around. Now, A and BC gases, if you compress them, the particles have a smaller volume to move around in. There are more collisions with the container, therefore the pressure has increased. So a pressure is a measure of the collisions gaseous particles have with their container. By reducing the volume, you've increased the pressure because these particles will collide with their container more often. So, what does this do with respect to collision theory? Increasing pressure increases the number of particles in a smaller volume. There are more collisions, more successful collisions, more products per unit time, and therefore increased rates of reaction. The dialogue is extremely similar to the previous example we looked at with concentration, so it's easy to revise. Increase in pressure leads to more particles in a smaller volume, more collisions. It's important to say there are more collisions, therefore there are more successful collisions. Don't forget that. And therefore there's an increased rate of reaction. Increasing pressure leads to an increased rate of reaction. Other factors increase pressure as well. I'm not going to get into that just now. I'll discuss that in a few moments. So, sticking to our collision theory, here I've listed the various factors affecting rate of reaction, which we're going to look at through the eyes of the collision theory. Increased concentration we've already seen in the previous part of this lecture. Increased pressure we just visited. Now, increasing the surface area. So, same reaction, A reacting with BC to produce A, B, and C. Here, I've tried to illustrate what happens to surface area. A diagram you may be familiar with in your books if you've come across it or your lectures. Let's say I have here a 10 centimeter cube. This cube, 10 by 10, is the surface area for just one face, is 100 centimeters squared. There are 6 faces to a cube. 600 centimeters squared is the surface area of this cube. Not the volume, the surface area. Now, I divide this cube up into 5 centimeter square cubes. I should end up with 8 of them, as I've illustrated here. Each of those cubes would have a surface area of 150 centimeters squared. Take your time to check that if you want. Times it by 8, the total surface area has increased 1200 centimeters squared. So, the smaller the particles, the greater the surface area. Therefore, if I was to make this into, say, a powder form, so lots and lots of tiny, tiny particles, which I've tried to illustrate with this diagram here, I would have a ginormous surface area. How does that affect rate of reaction? Because if I increase the surface area, there is more surface area for collisions to occur. With more collisions, there are more successful collisions, producing more products per unit time, increasing the rate of reaction. Again, my dialogue is very simple, so it's easy to remember. We can compare them and have the same sort of sentences. You've just got to tweak it a little bit. Here we're increasing the surface area. Before we increase pressure, we increase concentration. Here increasing surface area increases the surface area for collisions. More collisions leads to more successful collisions, leading to more products and therefore increasing the rate of reaction. Pretty straightforward, I hope. Let's look further at the presence of a catalyst. Now, in previous examples, we've looked at what's called an enthalpy profile diagram. We've also looked at the Boltzmann distribution. You may not have come across that yet. This is the Boltzmann distribution curve. Some of you will be familiar with this already. And this is an enthalpy profile diagram. I'm going to use these to illustrate what happens in the presence of a catalyst. So the definition of a catalyst. It increases the rate of a reaction without being used up by providing an alternative pathway with a lower activation energy. There are different types of catalysts. I'll go through those in the next part of the video. But for now, I wanted to generalize the definition, which applies to all catalysts, that they simply increase the rate of a reaction without being used up by providing an alternative pathway with a lower activation energy. Somehow, that activation energy is going to be lowered by this catalyst at a lower activation energy. So if we have here a distribution of energies, the Boltzmann distribution curve, showing that all particles in a specific sample do not have the same amount of energy, there's a distribution. And let's say this represents the energy that's going to be the activation energy. So all of these particles shaded in green can then collide and react successfully. All the particles to the left would have less energy than the activation energy, therefore would not react successfully, would simply collide and bounce away. Let's now add a catalyst, and in the presence of a catalyst, the activation energy has been lowered. This now illustrates a lot more particles have energy greater than the activation energy. All of these particles will now react. When they collide, they'll have energy greater than the activation energy. Successful collisions will occur. More collisions will occur that are successful. Therefore, more products are produced. Increased rate of reaction. These particles still have energy less than the activation energy. Therefore, they will still not be reacting. But the numbers that are reacting has increased because the catalyst reduced the activation energy through providing an alternative pathway for the reaction. That's caused an increased rate of reaction. Furthermore, on an entropy profile diagram, we can see the same effect. Reactants here, products here. That's the energy level of the reactants. Activation energy goes in, as illustrated here. Energy is then released, producing the products. Products have a lower energy than the reactants. It's a negative delta H. It happens to be an exothermic reaction. I'm simply illustrating what the entropy profile diagram is showing. Now let's add the catalyst. Activation energy has been reduced to the red curve. With a lower activation energy, we're providing an alternative pathway to get to the same products, for the reaction from reactants to products to occur. The delta H has not changed. That's the start, reactants. That's the finish, products. The delta H is the same. The only thing changing is the activation energy in the presence of a catalyst. So, in the presence of a catalyst, an alternative pathway for the reaction to occur has a lower activation energy. More particles with energy greater than the activation energy. Therefore, of the collisions occurring, a greater proportion will be successful. More products are produced and therefore increasing the rate of reaction. I guess at this point I can also mention, having a catalyst doesn't necessarily increase the number of collisions that would generally occur. Some were unsuccessful, some were successful. A catalyst has just lowered the activation energy and therefore provided more particles, now with energy greater than the activation energy, the chance to have successful collisions. I.e., the number of collisions hasn't changed. Of the collisions occurring, a greater proportion will be successful. Just to illustrate why I've worded my answer a specific way. So, catalyst, alternative pathway, more particles with energy greater than activation energy. Of the collisions occurring, greater proportion will be successful. More products are produced and increased rate of reaction. Let's now look at temperature. Temperature requires us to address collision theory in two different ways, leading to the same increased rate of reaction. I want to explain that a bit more. This here, again, the Maxwell-Boltzmann distribution curve, we have temperature 1 at a lower temperature, temperature 2 in red showing the distribution at a higher temperature. Here we see T1 is less than T2, lower temperature, higher temperature. What I'd like you to appreciate at this point is how these curves were drawn. T2, the curve peaks lower and to the right of T1. The area under the curve stays the same because the number of particles hasn't changed. And when I do my Boltzmann distribution video, you've either seen this or you're about to see the details of this Boltzmann distribution curve. But for now, I'm just summarizing T2, why it looks the way it does. Because of the way it ends at a higher level than T1, we now have extra particles with energy greater than the activation energy shown in red. So the activation energy hasn't changed, but at a higher temperature T2, more particles of energy greater than the activation energy. So At a higher temperature, more particles with energy greater than the activation energy, but also particles generally have more kinetic energy, so there are more collisions as well. So when describing the effect of temperature on collision theory, we say, at a higher temperature, particles have more kinetic energy, there are more collisions, and more particles have energy greater than the activation energy. Together, this leads to a greater proportion of collisions being successful, increasing the rate of reaction. I hope that's made clear sense.